So it was a very nice address, and everybody must have understood all the intricacies, particularly joints, and he has given the enough confidence for all of us to go ahead with the precast construction in a big way. I now quote here Professor Edmund Happold: "A world which sees art and engineering as divided is not seeing the world as a whole." Here is a professor who has seen both architecture and structural design to their excellence while constructing IIT Hyderabad. He is Professor KVL Subramaniam. He is currently professor in the Department of Civil Engineering at Indian Institute of Technology, Hyderabad. He was the Dean Planning and Development at IIT Hyderabad and oversaw construction of the new campus. Prior to joining IIT Hyderabad, he was a professor and cattle research fellow in Department of Civil Engineering at the Groove School of Engineering, the City College of New York. Dr. Subramaniam obtained BTech in Civil Engineering from IIT Delhi and PhD in Structural Engineering and Materials from Northwestern University, Evanston. After graduation, Dr. Subramaniam worked as a research associate at the NSF Center for Advanced Cement-Based Materials. Dr. Subramaniam was awarded the Early Career Award from the National Science Foundation of USA for investigating the early age changes in cementitious materials. He received the James Instrument Award from the American Concrete Institute ACI in 1999 for his research on non-destructive evaluation of concrete. He was the chairman, Committee 215 on fatigue of concrete of the ACI. In 2009, he was elected a fellow of the American Concrete Institute for notable contribution in the area of fracture and fatigue of concrete. He is an associate editor of the Journal of Materials in Civil Engineering of the American Society of Civil Engineers. He is on the editorial board of the Journal of Cement Composite elsewhere. He is a life member of the Indian Concrete Institute. He was elected a fellow of the Indian National Academy of Engineering, INAE, in 2021. I request Professor KVL Subramaniam to come over to the dais.
Good morning, everyone. Thank you, Krishna Reddy Garu, Prasad Garu, for giving me this opportunity to speak here. I think this is one of the probably 7th or 8th in the sequence of PEPSCON. It's an effort for us to promote precast industry. Of course, precast and pre-stressing go hand in hand in a lot of aspects that was presented in the previous talk. And of course, I'm here as the voice from academia, so the next few slides probably may be very pedagogical, but please bear with me. This is something we need to go back to the basics to understand that we are dealing with a technology which is suitable for India. We're on the cusp of very rapid urbanization, and we have a large demand for space, constructed space in our cities, and we need to do it very quickly, and probably precast has a solution for us. There are of course some pitfalls we need to identify, and also not get too carried away with the fact that we have information available without understanding the subtle nuances, without understanding the full extent of what has been done in the literature, what is reported in the literature, and what are the intents of the provisions given in the different codes. So that is the key thing. So let me see. Yeah, okay. Precast structures, I think my previous speaker, Mr. Sharma, did a very good job of introducing the precast structure, and I apologize, I missed the presentations yesterday, but I guess you had a full day of precast, so you already had your fill of precast. I'll quickly go over this. One of the biggest advantages we are touting with precast is of course the speed of construction. We can go very rapidly. Quality is supposedly a big plus. I use the word supposedly because it can also be a negative. Economy of scale. It works beautifully when I have modularity, where I can replicate the same structure again and again. That's where it works. And that's where I meant, that's what I meant by saying it is not a panacea. It doesn't work when you have architecture which basically demands different room sizes, different dimensions. It probably may not be the most economical. Where it works the best is where you have this economy of scale works out in the form of modularity, where things are repeated. There are also several challenges, and this is what I'm going to be focusing on, particularly dealing with continuity and load transfer. These are two things that we really need to think through when we're dealing with precast structures. And quality, which is supposedly touted as an advantage, can become a big disadvantage, because we come to expect quality, but if quality is not delivered in terms of material, in terms of the quality of the product, in terms of the quality of the precast element, it can come back to haunt us in the form of performance. So performance now becomes something that is very important, and we have to put our foot down on expecting performance rather than these prescriptive measures that we've been using so far. We have to master this. Yeah. So performance-based design, just to give a little bit of a background, what we've been doing so far is conventional method, which is more prescriptive. We rely on strength, we rely on something that we derive from loads, come up with a demand, and do our design based on that. But now we are slowly moving towards performance-based design, where the methodology or the structural criteria are based in terms of achieving performance objectives. So we want the structure to deliver a certain level of performance. Now, in terms of materials, I think what we're talking from a material perspective in terms of performance, we of course get a much tighter quality control, much tighter material control itself. So we supposedly get assured performance from the material perspective. And just a little bit of a side note, I think IS 456, our Indian Code of Practice, is now moving towards a performance-based design for material. Gone are the days when we would do concrete as a 1:2:4 mixture, or use. Looks like I'll be competing with this. Yeah, that's tough to compete against. Okay. Yeah, let's give it a shot again. It will be tough to compete with this. It's almost like a punctuation in my sentence. I'll keep going in between. But now, as I said, codes are moving towards performance, and this is coming even in material design. 456 is being revised. Now, concrete, the way we will be producing it will be for specific targeted performance in terms of its performance, not just strength, but performance in the long term. We will target specific durability performance for an assured life from the concrete. So this is happening already on the material front. Now, coming to performance from the structural elements which are made of precast. Continuity becomes very important, because after all, these precast structures are individual elements that are tied together, and it is how we tie them together that is important. How do we ensure that we can tie all of these individual elements to get a structure that is capable of resisting load? And loads come in different forms. We have the vertical loads, the gravity loads, and the horizontal loads. Now, when we're talking horizontal loads, up to a certain height, earthquake dominates, and beyond a certain height, it's all wind that dominates. And we have to be able to take care of both the gravity, the vertical loads, and the horizontal loads. And this is where continuity becomes very important. And the issues we're dealing with is continuity between individual elements, or individual elements that can form a member. So we can have one member that is made up of multiple elements. Of course, continuity between different members that make up the structure, and we have to identify the load transfer that is taking place in the structure. So in the mind of a designer, when we visualize a structural system, we have to look at how the load transfer is taking place, then visualize the continuity between the members and provide for that continuity in the load action between the different members. So this is just to basically just re-emphasize the point. We've all looked at Lego. We have these individual pieces, and unless we click them together, it doesn't form a continuous structure. And incidentally, this is a structure that is built in Germany that essentially looks like Lego, but it's made out of concrete. So just to tell you that we're dealing with something of this form here, where we have these individual elements that have to be clicked together. They have to be bonded together to make a structure. So in the next few slides, I'll talk about these building systems. We've already had the introduction to this. I'll primarily focus on the load path and the role of joints and connections. Now, of course, we have these skeletal systems. We were already introduced to this. We are talking about a beam column systems, and we can have the slab itself, which can be cast in situ, or we can have individual panels. Now, the question comes to if I apply a gravity load, the typical conventional gravity load path that we look at is that the load goes from the slab to the beam to the column and eventually finds its way down to the earth. Now, an example of a skeletal system, this incidentally comes from the FIB state-of-the-art report, and you can actually identify the different elements that are there. You can clearly see, in fact, we saw in the earlier presentation, you have the beam with the ledge, or it's a inverted T-beam, which is supporting these precast slab panels, which is framing onto the column with the corbels. So the load transfer becomes very apparent. The load comes from the slab, it is transferred to the beam, and eventually through the corbel, it goes to the columns. Now, this is rather straightforward, and of course, we've also looked at the wall systems where we have walls which are primarily intended as the vertical load carrying members. We can integrate them with the slabs to create these boxes which basically are quite stiff, and we can use that as our load carrying system. Now, that was the easy part when it comes to the gravity load. It's when it comes to the lateral loads when we have to put our thought into it, because now when we are talking about a horizontal load, something that is being applied to the structure laterally, we really have to be clear about the way this load transfer takes place within the structure. So we have to look at how is the load flowing within the structure. And in the case of a frame system, we are relying on the frame to basically, through the frame action, to be able to carry the load action. Now, this is rather pedagogical, and when we have a frame that is assembled with multiple units, we can actually look at how the gravity loads, what kind of load actions are produced in the members because of these gravity loads. And typically when we are talking about lateral loads being applied on the structure, just a frame structure does not have adequate stiffness. So we have to bring in these walls, which basically would be, and then we end up with a hybrid system where we have frames and the walls joined together to carry the loads, or we can have purely wall systems that can carry the horizontal, the applied lateral forces on the structure. And then the slab itself acts like a diaphragm, and of course then we have to ensure that the diaphragm action of the slab is maintained so that it is stiff in its own plane and is able to distribute the forces to the members, to all the vertical members in the building. Now, this is the most critical thing, is when we are trying to do this analysis, ultimately we need to analyze the structure for what are the member demands. And for that, I need to come up with an idealization, and that is I rely on a model. And building a model for a cast in situ structure is relatively straightforward because you assume the joint is rigid. So we rely on the stick model where the beams and columns are modeled as sticks, and we do the analysis. But this becomes a bigger challenge when we're dealing with precast structures, because as I'll show in the next few slides, the joint itself can have different levels of continuity, and that has to be modeled accurately, otherwise I'll end up with a different representation of the structure. So at some level, I have to look at the real structure, come up with an equivalent frame representation or some equivalent model representation, which I will analyze to get the member demands. That allows me to do two things. One is to design the individual members and also design the connections. So basically the flow of forces in the structure takes place through these joints, and these joints become critical in the structure. Now, if you look at the flow of forces and continuity in the structure, there can be different levels of continuity for a certain load effect in the structure, and that determines the member forces that I would be dealing with. So the level of continuity at the joints now comes into play, and this is something that I need to be able to address, and also to be able to model, to be able to determine the member demands. Now, when I talk about levels of continuity, this distinction actually is very nicely presented in the FIB state-of-the-art report. And probably that is the most concise of all reports that I've seen. And they make a distinction between a connection and a joint. So a connection is where you have two structural elements which are basically which have two different types of load actions that are coming together. So in this case, we have a connection between a beam and a column. A beam is conventionally designed for flexure, a column would be carrying flexure in addition to axial load. So these are the two load effects that we have in these two structural elements, and they've come together at this connection. But then within a connection, we can have multiple joints. So we can have a joint that is transferring shear force. We can have a joint for transferring moments. So basically, they have separated out what is being transferred at a connection. What is the load effect that's being transferred from one member to another at a connection. And this is where precast is probably more attuned to design, or more similar to designing of steel structures. Typically, when we design steel structures, we have these members, and it is how we design the connections that determines what is going to be the load effect in each member in effect, because ultimately we have a structure and the load gets transferred from one member to the other, and the load effects that are produced in the structural element then depend upon what is the transfer that is taking place at the joint. So we can basically have different levels of continuity in our joints. We can go from a simple shear connector to something that is able to transfer moment partially to having something that has full moment transfer. And this is all, we can do this in precast design, much like what we do in steel design, where we can have partial fixity or we can have complete fixity. It is up to the designer to decide. And of course, there are consequences of this. As shown beautifully in this picture here, this is again from FIB, where if you have basically at the joint, if you allow the rotation between the beam and the column, you basically would have no moment transfer that is taking place between the beam and between the support beam and the slab. So this I can do with a simple shear connector at this joint, but of course then I have to prepare for higher bending moment, which is in the positive sense in the slab that is, or in the beam that is the horizontal beam. But now if I enforce fixity there, then of course I have to prepare for this moment that is being produced, and in addition to that, a different load action for the member. So these are all consequences of fixity that I get depending upon the joint that I design. So this now becomes integral to our thought process, where we have to think about the joint itself. What kind of load transfer am I going to provide, and a consequence of that on the forces that are produced in the beam. Now of course we've seen this before. So if I decide to go with simple shear connectors or simple shear load transfer, gravity load transfer at the joints, those become simple shear connectors, and basically it is like a pinned connection. The consequence is the columns now act in a cantilever manner. I get a much softer frame because now the cantilevers can deflect considerably. And if I ensure moment continuity at the joints, now the beams start participating in the total load action as I push on the frame, and I get a stiffer frame. But of course, then I have to deal with the beams being bent in double curvature. So that is the effect that I have to consider in the design of the beams, and of course also be able to provide that level of continuity to ensure that I get a rigid joint between a beam and a column. And whenever I'm talking about providing adequate horizontal resistance, I have to bring in wall systems. I can have bearing wall, which is part of the facade, that is also contributing. Or I can have a braced skeletal system, where I have a skeletal system, beam column system with a shear wall, which are acting integrally. Of course, there I rely on the horizontal, the immense shear stiffness of the wall to carry the horizontal force. And then of course, we have to look at the load transfer between the different precast wall elements. And depending upon what level of continuity we maintain there, we can have different kinds of wall systems, including the ones which are now being called as the supposedly damage-free structures. So why is this horizontal force important? Primarily from earthquake and wind. And our previous experience from precast structures and earthquakes has been mixed. We have had very good performance, or earthquakes, the precast structures performing very well in earthquakes, and fundamentally they should, because typically precast buildings are very regular in their geometry, and they are very symmetrical in plan layout. Those are the kind of structures that we build with precast. So they have a very uniform distribution of mass and stiffness elements. So they would actually behave very well under lateral loads. And these typically have better quality concrete. So there's no reason for these structures not to behave properly. Where they have performed poorly is because of brittle non-ductile connections. So the Achilles heel of precast structures is the connection. If we can design, detail the connection properly, if we understand what is the load transfer that is taking place at the connection, then we know how the structure is going to behave and make adequate provisions for accommodating whatever is expected from the structure when it is subjected to an earthquake force. Poor detailing of elements has been reported as a cause, and poor design concept where the designers have not visualized as to what would be the load flow within the structure when it is subjected to horizontal forces. So again, when we come to the design of a precast structure, we have to be able to visualize the flow of forces. We have to be able to design the joints, anticipate the kind of continuity that we want, and prepare the elements to be able to carry the kind of demand that is coming their way. So just some photographs, and invariably you would see that it is the joints that have failed. The structural elements have simply been deseated, or they've been uprooted from the connections and they've fallen off. More photographs from near here. Schools that are built in Bhuj, a lot of them were precast. Essentially the elements were intact, it was the connections that failed, and the slab beams were unseated because they were not anchored properly, and you can see the elements are relatively intact. They simply got unseated from the connections. So for lateral load response, what we need to do is understand the failure of joints and be able to address this progressive collapse. And this happens when let's say failure happens in an isolated part of the building, and if that part is to fail, the load redistribution happens and the remaining members in the structure are not able to handle the redistributed load. So this is something that we need to be able to address, particularly for precast buildings, and sometimes this becomes an issue during construction. It is not just after construction, because during construction is when the precast building is at its weakest. We have not still assembled everything, the boxes are not all tied together, all the units are not tied together, and these individual elements still don't act as a unit with all the other elements. So we can potentially run into this progressive collapse during construction, but this also has to be addressed later on during an earthquake event. And the basis of most of our codes is the same thing, continuity requirement. We have to make sure the elements are continuous, and shear and flexure at joints. How do we take care of this shear and flexure at joints? And there are different joints that are given, different methodologies that are proposed, and but the fundamental principle is very straightforward. What we rely on is, suppose there is a horizontal force, suppose there is an earthquake. Now we rely upon the nonlinearity that is generated at a few locations. So we pre-identify those locations where we expect the nonlinearity to develop. And so typically these are identified with flexural hinges. So we identify flexural hinges. These hinges are supposed to form at predefined locations. And the way we define the hinge is that it should be able to carry the load without much strength degradation over a long displacement. So that is the whole idea of this ductility. And we wish to have all our joints to be ductile. And then while these hinges are forming, we want to make sure that the other elements are strong enough that those don't give way, and they basically allow the hinges to form at the predefined locations. And typically when we want to have nonlinearity, we want to have energy dissipation, we would ideally have it in the form of a flexural plastic hinge. That is the best way to dissipate energy. Shear is not the mechanism that we rely on. And these plastic hinges are localized at the beam column joint. So that is the key. Even for reinforced concrete, that is where we expect our hinges to form. And when we're talking about these precast connections, of course, we're talking about detailing requirements of the plastic hinges would be the same as those established for cast in place concrete. So this is the fundamental requirement of precast concrete. That is, we expect the precast structures also to form these hinges, and the requirement would be the same as what we would have for cast in situ concrete. And the basic understanding of this is when we look at the lateral response or the response of a structure to a horizontal force, we rarely design a system to be linear elastic up to failure. These are systems of limited or no ductility. We do want structures to be ductile, that is, they're able to deform, and we design the structure for a reduced capacity, but of course assuming that it can deform a lot. We use the strength reduction factor, and the entire concept is of course called the capacity based design. And one thing to realize is that the strength reduction factor itself is a complex combination of multiple factors that includes ductility, strength, damping, and redundancy factor. These are built into the codes, and we come up with different factors based on the expected ductility from the system. So now when it comes to detailing for ductility, we are basically requiring that all the plastic hinges should form at the predefined locations, ideally in the beams or at the beam column joints. And so for our precast structures, we would want that our longitudinal reinforcement should be continuous across. I think that was also presented in the previous talk. We would want the continuous, the tensile reinforcement, both top and bottom, because we may have moment reversals to be continuous across the joint. And when we're dealing with the wall, ideally we would want flexural plastic hinge to be formed at the base. We don't want shear failure in the wall, because that would lead to this localized deformation or a story shear, which is highly avoidable. And when we're detailing for the diaphragms should be able to collect the forces, transfer them to all the vertical elements. That is the requirement of the diaphragm in this entire building system. And of course, the fundamental thing in this capacity design is we have an estimate of the time period which we use to estimate the demand. And usually it's an empirical formula where we relate it to height. And this, when we're dealing with regular reinforced concrete structures, often leads to an overestimate, or basically the time period we get from this formula is usually much smaller than the real time period of the real structure, and that leads to an over design oftentimes. But in precast structure, because they're inherently stiff, this actually does a pretty good job of estimating the time period. So it's not so much of an over design. So when we're coming to design of precast structures, we really need to look at this formula if we are still going to use this as the basis for scaling our responses. Because the time period that we get from here is actually quite a good reasonable estimate for precast structures, particularly for the wall-based structures. Now, there are several codes of practice that you would see. You have, and of course, different manuals that are available. The PCI connections manual is a beautiful manual where you have different types of connections that are detailed with detailed calculations on how to go around designing different types of connections. The Canadian manual, then the FIB. I think these are probably the most comprehensive piece of work that I've seen. You have the FIB guide on connections and the state-of-the-art report, a must-read for those who are looking to get into precast, where the theory behind a lot of these things is explained in great detail in both these documents. Then of course, we have recently in India introduced the code for prefabricated building. It was much overdue. It was a significant overhaul compared to what existed. Of course, this deals with prefabricated buildings, IS 15916. And here we're dealing with partially or fully assembled erected buildings with structural parts consisting of prefabricated individual units or assemblies. Now, I'll just quickly go over the different provisions. I don't want to get into details of these provisions, just to show that significant advances have been made. Of course, there's still several things that need to be done. One, of course, we now introduced this basic module, which I think was desperately needed, because if we are going to look at precast elements as manufactured products, we have to treat them with the respect of a manufactured product, and we need to introduce tolerance requirements. Now that modules have been defined, the tolerance requirements have been specified. Then resistance to horizontal loads is specified. It's of course provided that the resistance to horizontal loads shall come from appropriate moment and shear resisting joints. So the joints play a key role, or placing shear walls in the structure. And it says precast structure should be analyzed either as an emulative or a jointed system, and we've already seen what those two systems are. But of course, the level of detail given on jointed systems in the Indian code is very limited. So although they talk about jointed systems, not much is described in the code on jointed systems. The component level designs, everything, basically you are referred to loads, which to other IS codes. And when we're talking about precast components, this particular code refers you to other existing codes on specific elements. So if you were to design hollow core slabs, it refers you to IS 10297 and so on. So there is basically now a good connection between this code and the other codes for other precast elements. Design and handling is something that is mentioned when you're talking about precast elements. The precast elements themselves should be able to handle the stresses during hoisting and erection. We have to account for the different stages of construction when we're talking about hollow core slabs. When we put the hollow core slab on a structure, it should be able to handle its own weight in a simply supported arrangement. But once we put a composite deck slab on top of that, the live load itself is taken by this slab system would be taken in composite action. So the change in the action between a simply supported hollow core beam taking its own weight and the weight of the live load and any other imposed load being carried in a composite manner with the deck slab. So that has to be accounted for when we do the stress analysis. Now, I'm switching gears because this level of detail is not available in the Indian codes, and we don't have such design charts. I just wanted to show you that PCI has these design charts that are available, which are basically like cheat sheets, which allow us to decide on the spans that would be required, the depth of the hollow core elements. And these charts are available for different types of geometries. Of course, these are all proprietary systems, but for these proprietary systems, we know exactly if I have a certain span, I can simply look up the chart and decide what is the thickness of the hollow core slab I use for this particular span and for this particular geometry. And of course, PCI also gives us these nice design charts when we have, let's say, a composite system. So here for this particular 6-inch hollow core slab, if you look at the solid lines, that tells you the range for a given span and superimposed load. What is for a given superimposed load, how much span can you use? And once you make it composite, you move to the dashed lines, it moves to the right. So such charts are available that basically simplify designs, which of course, unfortunately, if one is to use the PCI design, one has to get used to the Old English unit. Now, not just that, there is a fundamental difference in the design philosophy, and this is something that people should be aware of. Our method of design that we use is predominantly the old British method, whereas the Americans follow a different design procedure, notionally different when it comes to the way that they calculate the nominal capacities. Then of course, when it comes to design of individual elements, you have enough ways of designing it. You'd fall back on IS 456 for design, but of course one has to get used to seeing these beams in a different configuration. Being an instructor, I always teach my students to design T. It's very difficult for me to tell them that it can also be used as an inverted T. But this is an example where I can basically tell my students, look, it's not just an exam problem, it happens in real life. So the first time I gave such a problem in the exam, everybody thought I was out to trick them. But then this is reality. We do have inverted T beams that do come into play when we're dealing with precast structures. And of course, one has to get used to corbel. A corbel is a nice element to have, but a high shear element. It should be designed and detailed properly. This can turn into a weak point of the entire structure if it is not designed properly. Now, the last thing I want to touch upon is continuity. When we have all these elements, it's not just that they're connected, the joints, we have to make sure that the entire structure is continuous, and for that we have these ties that have to be provided in the structure. We have to provide ties in the periphery, which basically ties all the elements together, internal and vertical ties, to make sure the entire structure, these are like rubber bands that are holding the structure together. And of course, we put peripheral ties in the slab, where we basically at each floor and roof level, these continuous ties are on the periphery just to tie the slab together. There's a prescriptive requirement that's given in the code, and similarly we have internal ties that need to be provided in the structure, again just to ensure that there is this stick that ties everything together, and there is a prescriptive requirement given for that. So finally, we have this emulative detailing system. So the code talks about this connection detailing, which is emulative. That means we are connecting two precast elements, and the connection is as if it were made of cast in situ concrete. That is what we expect from an emulative connection detailing. What is given is in Annex C in the code, a whole host of connection details are given. Now, it is presumed that if I am to follow one of these levels of detailing or one of these connection details, I am producing an emulative connection. But the actual fact needs to be checked, and that leads us to the final thing about this code and ductility. Now, when it comes to design and detailing of regular reinforced concrete structure, the procedure is very straightforward. We do design as per IS 456, and we do detailing as per IS 13920, which assures us the added ductility. Now, that link per se is missing in precast elements because we presume ductility of our connections. When we do a connection, we don't know what is the level of ductility that's available. And while all codes talk about the requirement of ductility, the exact ductile detailing requirement for precast is not exactly covered. So this is one of those gray areas where we presume that if I follow the code, if I do an emulative connection, that I am achieving the level of ductility, not just the strength, but also the level of ductility that would be required. And for surviving an earthquake, it is the ductility that is important. I need my structure to remain ductile. And that is still a gray area when it comes to these precast structures. That is the connection and the level of ductility that is achieved with these different connections. So with that, I'd like to conclude and thank you for your attention.
Thank you, sir, for a wonderful lecture. And he has covered almost all the provisions of the codes and the practices which are prevailing. Now I request Mr. Sagar Patel of PSP to come over and present memento to Professor.